Recording is on.
Okay. Good morning, everyone. So, it will be good evening for you. So, let's discuss some of the problems on the heap today. I'm going to share the screen here. Okay. Can you see the screen?
Yep.
See, okay, I need to get into the other monitor. Okay. So now, last week we discussed about the building a binary tree using array, right? It's very important concept. This is how to navigate, how to create a binary tree just using a array, right? So last week, you guys remember, right? So we did all the pre-order, post-order, everything in the inside the array itself by using recursion, right? And we also discussed about the path to the parent. So given a node, just to start from anywhere, like start from fifth node or the kind of index, and we can go to the parent using this formula. You guys remember? Do you remember this formula? Parent going to the parent node.
Yes, yes.
Yeah.
Yes.
So node index minus one by two. That will give you the index of the parent inside an array, right? So if array is like this, you can navigate to the parent node. So that will be helpful to understand the heap concepts. We also discussed about heap last week, right? So I think this is the heap, max heap, min heap. So min heap, as we discussed, min heap means the minimum element will be on the top. So at any point of time, so minimum will be on the top, and if you go here, so next minimum will be either left or right. So that is the main. So parent node value is less than child node value. That is only the relation between parent and child, right? Yeah. If you look at these two, 10 and 25, so 10 will be on the top. So similarly, max heap is the reverse. So top element is the max element, and childs are less than the parent. So this is how it is, right? So let's implement. So how to implement the heap? Because of course there might be C sharp or Java. The latest languages might already have a heap data structure, just like stack or queue. They have I think priority queues. They call priority queue or some different terminology, but this will be already implemented in most of the major languages that we use. But how to construct ourselves? Just like we did, like stack using queues, stack using arrays, right? So similarly, using arrays, we can implement this heap. So we already discussed, right? So now we are going to discuss how to implement. Okay. So there are different operations. If you look anything like any data structure, what are the main basic operations? The main purpose of data structure is to store the data, right? So what are the operations we do in any data structure? What are the basic operations?
Like sorting techniques, we do sorting.
Yeah, no, data structure, just sorting is another thing you can do on top of data. Let's see, if I give you the array, we can sort the array, we can sort the linked list. That is also an operation, but the basic, just the general thing is, if you have a data structure, what we do. So basically,
Trans-
go ahead.
Uh,
Transfer
point.
data structure, going to the end of the data structure, retrieving a data, inserting a
Exactly. Inserting a data, retrieving the data. Exactly. That's a
Oh,
basic operations, right? Yeah. So first one is inserting a data, okay, and the second one would be deleting the data. So when you are creating a data structure, the main purpose, either it could be hash table, array, or trees, or bind, any data structure. These are the basic things. We want to put the data and we want to retrieve the data, correct? And also sometimes we want to delete the data. We don't want the data. Let's remove it. Let's say this is the number of employees, or you can have anything in the data structure, right? So instead of numbers, let's say these are all employee objects. One employee resigned the company. You want to remove that object from the data structure. That's a removal. is another operation. And another operation is iteration. We don't want to remove, we don't want to insert, we want to just iterate. Iterate means basically visit each node and display the data, right? So display or any operation, you want to give a hike to every employee, right? Let's say you have a tree or a heap with 100 employees objects. You need to go to every employee and you want to give some hike for the salary, right? This kind of operation, you are iterating every node of the tree, and you are doing some operation inside that object. You're not deleting the entire object, at the same time you're not creating new object, right? So those are the operations you can. What are the other operations? As Vanilla said, we can retrieval is a process where every data structure allows a kind of different type of retrieval, right? Linked list allows a retrieval all the way from head node to the last node in a sequential way, what based on the links, right? If you look at the array, it's up to you. You can iterate. The main advantage with array is you can iterate anyway. You can iterate from start to the end, or end to start. You can use the index, right? So you can also use, like, by using the indexes, you can also jump around. That's what we did last time, right? Excuse me. So last time we did the binary tree using arrays, right? What we did here, we are just jumping around here and there, right? If you look at pre-order, we started with an index and we are jumping into the next index, right? It is the same array, but we want to navigate in the form of tree. So that is the main advantage with the array is you can navigate whatever the way you want, as long as you are between the indices. We are good, right? Are you guys following so far? So
Yes.
So this is a retrieval, right? So as Vanilla said, we don't want to follow this order. We want to follow sorting. We want to retrieve the data in a sorted way, right? So sometimes another questions is like, I want fifth maximum. I want, like, this is an example where the heap will be very benefit, very useful. Let's say you have just any data structure. Let's say you have a linked list with 1,000 elements. Okay, 1,000 random elements. They are not in a sorted order. They are just a linked list of elements. Okay. Now the requirement is we want 60th smallest element. That means not smallest, it's not biggest. I want six, like, let's say 100th smallest element. You have 1,000 elements, right? You want to know the first smallest. The smallest, right? Like, smallest means the number which is less than, without, compared to any other number. Second smallest means the second number which is smaller after the first number. This who is the second number, right? So similarly, the requirement is like this. You have 1,000 elements. I want 100th the smallest element. So how can we do this? In a normal way. In a normal way, what we can do? So we have to, let's say, if you I don't know whether you remember finding a min element. Let's say finding a minimum element in an array. What we do in a basic algorithm. So very simple. Let's say you have element of 10 elements in the array. You want to find min. What we do?
So
And
we
we
take.
number each and every element with one element which is picked up in an array. If it is
In
not sorted,
If it is, it's not sorted. That's the main thing. If it is sorted, there is no point. If it is sorted increasingly, you will take the first one. If it is sorting decreasingly, you will take the last one. That's very easy. The thing is, do you have an array without any sorted elements, the randomly there? You want to find a minimum. What do you do?
for each element, the min element will get changed while comparing with the adjacent
Exactly.
elements.
Exactly. So what we do is, maybe we will first initially assign min with the first element, or maybe in integer dot minimum. You can also take integer dot minimum value, like, which is very smaller than any other number in this, right? Probably there will be integer dot minimum also there. That should be fine. Either we can take the first value and say that is minimum, and then we will compare with minimum with every value. Correct? So, and if you find a smaller value, what do? You will swap it. Now this is the smallest. We will assume that, let's say you have 8 here, but you found a 5 here. which is smaller. All these other numbers are greater than 8. But once you come here, you found a 5 which is smaller than 8. Now you assume that this is minimum, right? Now from here, you will start comparing with that 5 with every other element. This is a finding a minimum, right? Now, if I ask you find second minimum, I don't want first minimum, I want second minimum. The second minimum, okay, I can maintain like a first minimum, first min and second min. You can have two variables. You can compare like a first variable here, second variable here, and like you can maintain. This is kind of relatively okay kind of thing. You can maintain, like if I ask you third minimum, you can also maintain three variables. But if I ask you like 100 minimum, how can you cannot define 100 variables in your program, right? Even if you define, on the next day I will ask you, hey, what is the 150th minimum? Then your program will break.
Yes.
So that is the main problem with the array data structure or any existing data structure which is not giving. Only thing is the other option. What is the other option? The other option is sort the entire array. Okay, if you sort everything, then if you say second minimum, here is a second minimum. Let's say all are increasing order. Okay, so this is a bigger number here and smaller number here. So you already sorted. Once you sorted, what happened? If you want second minimum, here is second minimum. If you want fifth minimum, 1, 2, 3, 4, 5, here is a fifth minimum, right? So it is easy. Once you sorted, it's easy. But the problem with this sorting is you sorted, you have 1,000 elements, you sorted, and now you remove one element. If you remove element, it's array again. You need to adjust the elements in another. So again, let's say another element got inserted. Again, you need to sort it. You cannot add at the end, right? So it could be tree, it could be linked list, it could be anything. If you are sorting, right, every operation, the insert operation and delete operation requires you to sort again. If you are inserting, so you have 1,000 elements, you inserting at the 5, you want to insert 5. Let's say 5 is not there in these 1,000 elements, right? So either you have to insert at the end and then resort the array, or maybe you find exact element and put the 5 at the exact place and shuffle rest of the elements, whatever it is, right? By the end of the day, after inserting 5, now I should be able to get 100 minimum. I can simply go to that 99th place, right? That is the 100 minimum, correct? Because if you already sorted, it doesn't matter after removal, after insertion. If you are keep sorting your array, we'll get the minimum element, minimum or maximum, whatever. So you need to sort the elements all the times. But the sorting means like you are processing all the elements. But in case of heap, we already discussed last time, right? So this is the heap data structure. So you can insert anything. You can insert any value. Here is the thing. See this? You have values like this. This is a min heap. Okay, you have 3 at the top. There is no other small number other than 3. Of course, we just added 1. If it is a normal array, as I said, we have to sort all the elements. But the advantage of heap is we don't need to sort the elements. We just need to replace these elements. See, so after inserting 1 in the above heap, the min and max property of the heap is distorted. Basically, so min is not on the top, right? So min is at the end. So usually we will add at the end. Now we need to do swapping of the elements in the above heap. We need to do the swapping. This is called bottom up heapify. So you are heapifying from the bottom of the tree to the top. Look at this. So first step is you'll compare. You just added 1. Compare with its parent 19 and 1. Which is smaller? 1 is smaller. If you find smaller, and then small will go up. That's the min heap, right? Small will go up and a bigger number go down. So 19 comes here. Correct? Now 1 is here. 1 and 5. Compare 1 and 5. 5 is greater. And then 1 goes here. 5 comes to here. Right? Now 1 is here, 1 and 3. You'll compare 1 and 3, and 1 is smaller. Then 1 goes to the top of the tree, and 3 comes to here. So how many elements you touched? Literally one, two, three, four elements, right? So you did not touch, you did not even compare with any other elements. But sorting, if you do bubble sort or quick sort, you have to touch every element. So here the heap sort is like in this sorting algorithm, we are just touching the parent elements. Is it clear?
yes.
Yeah, that's the advantage. So after inserting one, you still are sorting. The same thing is just like array or linked list. You are still maintaining after inserting or after deleting. We need to do some operation to make sure our array is in a proper way. So our main purpose is like this. Our main purpose is we want minimum very fast. Min heap is like this. So if you frequently asking minimum value, if you frequently asking minimum value, you maintain the min heap rather than maintaining a linked list, rather than maintaining any other tree, binary tree or arrays, normal arrays, okay, or any other stacks or queues. You don't give stacks or queues, never give any min or max, right? The stacks and queues will give you in a particular way of insertion, like you are inserting and then you will retrieve based on the particular order. It never. So sorting, you can start in a stack also, but it's a lengthy operation. It's very lengthy operation. You cannot sort easily in stack or queues, right? So this min is still using arrays, but using this specialized form of replacing the elements or the sorting technique, you know. So we'll maintain the minimum at the top of the array, top of the tree. Okay. So that this is called bottom up heapify. Okay, we are heapifying or just changing the from bottom to the top, right? So now let's assume that we want to remove basically. See, here is the final tree. Basically, after inserting one, see this one came here, three here, 5 and 19, right? So now this is the algorithm they gave. I wrote the same algorithm in my notes here. So now extract value from the heap. So another, let's say we got the exact same tree again, back to the normal given tree. 3 is on the top. So we want to remove the three. What we need to do? We need to put the next minimum on the top, right? So we want to put the next minimum, either it would be 5 or
Fine.
8. Exactly. So that's what we need to compare. If in the above example, 3 is the root node and we have extracted. So basically, so 3 is extracted. So we need to replace 3 with the least element in the tree. So the way to do is basically, you know, so that's what these guy like the idea here is we will take the last element and put it on the root. So now 100 will become the root node. When 100 becomes the root node, the min and max property of the tree is not maintained. So we need to replace the elements in the tree by swapping elements from top to bottom. So this is way to do. So why we need to do like this? Because it's all in the array, right? So let's take here. So the we are maintaining a heap in the form of array. So we are maintaining array in the form of array, and the first one is always, this is the zeroth element, always minimum. This is the minimum, and its children will be here and here, right? This will be next minimum, and these children will be somewhere in this arrays, right? So we want to remove this, and we want, instead of, if you remove this, we need to put the correct value, right? So the easiest way is put the last value, whatever anyway. If you remove it one element, definitely the elements need to be shuffled, right? Put the last value in this location and start heapifying from top to bottom. This is top to bottom heapify. So you put the 100 there and compare 100 with the other numbers. See this. Here is 100. We have 5 and 8. So now we will compare what is the small number, right? Hey, Aravind.
Hello, Suresh.
Hey, Aravind. Yeah. So we,
Sorry.
we are just discussing. Doing good. Yeah. How are you doing?
Yeah, I'm fine. Thank you.
Good. So can you see
I'm a
my
bit late today. Yeah, yeah.
No, no problem. So we are just discussing the same concept what we discussed. The heap is really important, and it's also complicated as well. So last week we discussed about heapifying, from top to bottom to top, right? When you insert, heap, we discussed about heap last week, right? So
Yes.
when we insert a node, we will insert at the end of the tree, and we will do bottom up heapify. So we'll compare with root and then exchange. That's what we just discussed, just now. So we'll compare 19 and 1, and then 1 goes here, 19 comes here, and then 1 and 5, 1 goes to this place and 5 comes here, and then finally 1 and 3. Finally, the 1 will goes here. That's because we are building a min heap. So going from so even if you look at the complexity, right, it's order of log n. Yeah, see this. So we can also discuss complexities for everything. So this is really nice article here. So peak of the heap, if you want to peak the first element, just order of 1, right? If you peak means like getting the who is the smallest element, or getting the smallest element is very easy. You don't need to navigate anything, just take the first element. Okay. And complexity is order of 1, just looking at the first element. Of course, they are saying order of array of 1, but in C sharp it's array of 0. Like index starts with 0. In this particular, he says like C sharp, but C sharp maybe he is using 1 as the first element, but index starts with 0. So size of the heap, how to get the size? This is also order of 1, because just get the size, length of the element, or number of elements in the tree. But this one is order of log n, because after inserting, right? So inserting a value, order of 1, we are inserting at the end. And finally, so heapifying, bottom up heapify. This is the main important thing. When you add 1 here, it will go to the height of the tree. Height of the tree is always log n. That's what the complexity. We are not touching any other elements in the tree except this parent, path to the parent. We'll only touch the path to the parent all the way to the root node. That's why the bottom to top heapify is basically order of log n. So which is greater than any other order of 1 here. All the operations of order of 1. So that's why the overall complexity of inserting element is order of log n. So now extract element. Now how to remove the element? Okay, you are going to remove it, right? So how to remove it? So if you remove 3, right? So the best way is to uh, find what is the next. Put the 100 on the top. Put the 100 on the top, and then do the top to bottom heapify. That's the process here. So we will put the 100 there, and then you will compare which one is bigger, right? So then 5 goes here. 5 is the smallest one, right? Which is smaller. Basically, you need to find the small one and swap it. So 100 goes to the 5th place, and then 117. 17 goes there, and then 25 goes there. Finally, 100 comes here. See, 100 was initially 100 is the left node of right node of 17. Now 100 became the left node of 25. That is how the things will work. Is it clear? So this is the basically top down heapify. You're starting from the top, and and then you are comparing with the rest of the children. This is also same thing, order of log n, right?
So in this, Suresh, in this, will array will be provided, or how? Suppose if in the example that they given, will they
Yeah.
give an array and we need to convert into heap, or how will be the question will be?
So I don't know whether this is a concept of the heap. I don't know whether the interview questions will whether they ask you to build a heap. They are asking if they really ask like this, build a heap using array. Build a heap. This is a heap, right? So last time we build a binary tree with array. You remember, right?
Yes, yes.
Last time we build the whole tree with a binary tree just by using array.
By using
So
array.
yeah. So similarly, there could be a question like this: build a heap, build a min heap using array. This is the simple
Okay,
question.
means because I'm just thinking about, suppose if they gave an array, and
Mm.
if we want to take the but they like a heapify from top to bottom,
Hmm.
then we need to take the max element. To get the max element again, we need to have an iteration of that array,
Yeah,
and there will be log of n.
yeah,
And
order of log of n. Yeah, because we don't compare with every element, right? Yeah, go ahead.
Yeah, so there the complexity to get the hundredth element, hundredth like the max element or the value of 100, we need a log n, and from the log n again there will be some iterations like, so the total overall the complexity will be more log of n plus something. Log of n, is that true? I don't know.
Yeah, that's definitely a good point. Yeah, you're saying like that's a basically two algorithms. First is building the heap, right? And then
Yes,
getting the 100th the smallest element, or getting the 100th maximum element, right? 100 small, because we are implementing min heap. You can get the 100th the smallest element, like first smallest, second smallest. Let's say the question is get the 100 smallest element. You need to traverse how many elements?
hmm.
100,
Yes,
elements, right? 100 times. Basically, you have a tree. Once you have a tree, like once you have a tree like this, right? So if you are keep removing values 100
yeah,
times, then that will be the 100. You will get the minimum value. You will get the after removing 100 times, what will happen? The top will be the next minimum, right?
yes.
So that will be the, like, if you are removing hundredth the time from the tree, that is the hundredth minimum of the in the whole given input.
Okay, okay. So
Yeah,
generally, if there is a sorted array, then won't be any issue, right? So if the sorted
yeah,
array, the max element will
it
be
is
the
sorted.
last element.
Exact. Come again. If it is sorted.
If a sorted array, in this the same example, for example, we need to remove the three.
Mm-hmm.
We need to remove this third node, means the first node, and we need to sort it, right? So in this we need to pick the 100th element, and we need to place that in the first position, and need to make a sort.
Yeah,
So
we are sorting. We are not sorting all the elements. We are just sorting based on the values, right? So we are not taking 100th element. We are just taking the last element value. The 100 is the
yeah,
value
yes,
of the last element. So how
yeah.
many elements we have? One, 2, 3, 4, 5, 6, 7, 8, 9. We just have 9 values,
Okay.
right? So
Suppose
now,
if we have, sorry,
yeah, go ahead.
suppose if we have nine elements in an array,
Mm-hmm.
the given example, we have a nine elements in array, so
Yeah,
we need to remove the first element, and
exactly,
we need to make a sort, like
exactly.
the structure, like heap structure. So
Yeah,
in that if there is an array, first of all we need to build the heap, and we need to do the process, right?
exactly, exactly. So when the given array is like this, okay, this is the array given like this, okay.
Okay.
So, but the first element is not the smallest element. By looking at it, you can see what is the smallest. One is the smallest, right? So
Yes,
once you build the heap, the first element, this is the root, is always the smallest. You know that. So that's
yes.
why whenever the given array is like this, we need to first heapify do the heap, build a heap out of the array. So like, this here is the thing. See this? So
Okay,
in heap, I'm going to explain the algorithm. So first, with the given values, let's build the heap. So we can do this actually instead of let's do that exercise so that it will be so easy to understand. So it is complex, topic, but let's follow along. So what is the input here? Let's talk about the input. Okay, so here is the input, right? So 9, 9, 8, 2, 1, 3, 4. This is the array, given array. Okay, so how many elements we have? 6 elements here, right? So now the question is like we need to first build the min heap, and then we need to take the, let's say you want the first min, we want just first min or second min. If I just ask you like we have 6 elements, if I ask you fifth min, So you can simply should be able to give that using the min heap. So what we do with this one? So first we will create the how to build a min heap. So building min heap, we need to provide these are the operations as I said before. First one is the insert, and second one is the delete or the peak or get the top. So anything, whatever the name of the function, either it could be delete or get min, because we want to delete only the first one, or you can also say get top. So whatever the value, whatever the name, the main purpose of this function is just to take the first element from the min. If you have tree like this, so you just remove the first element. That is the thing. And also length will be there. So you want to know how many elements in the heap, right? So what are the other elements? I think these are the functions. I think these are the functions we can write. So now let's talk about insert, right? How to build a heap out of this. So initially you gave this array. So we are going to build a heap. So we need to insert each element. Let's say you have a heap. Let's insert 9 into the heap. Currently the heap h equal to null. Okay, there is no trees, there is no elements. Once you get the 9, what you do? Just put the 9 here. How many nodes right now? Only one node. Now let's insert 8. What do you do? So once, as the process, as I said, let's go through the same process as I explained in the algorithm here. How do you insert? You're inserting, first you will insert as the last node in the sense like just insert as a child node of the whole tree. So here is the whole tree is just one element so far, right? So we will insert as a left node usually, right? We will first insert as a left node. Now you do bottom up heapify. That means start from the bottom, start from the last node and heapify. Once you heapify, what will happen? This whole tree becomes like this, right? 8 on the top because that's a min, and 9 will be here, correct?
Yes. Yes.
You get just two elements right now. So inserting 8 is two operations. First one is inserting at the last, and
Yeah.
then doing the bottom up heap phase. This is bottom to top. Let's say, yeah, bottom to top heapify or bottom up heapify. So you can call anything. So now insert 2. Let's insert 2. So if you are in a array format, right? Array format is something like this. 0, 1, 2, 3, 4, and 5. So in an array format, initially you inserting at the, so you insert a 9 here. Okay. Now when you insert 8, you insert 8 here, and then we will heapify. Then it becomes like this. So 8 comes here and 9 comes here. Okay. Right now. Okay. Now you're inserting 2. What you do? This is our heap. As I said before, just insert 2 at the end of the array and then do the bottom to top heapify. Correct? So now what happens? We compare only these two. Which is smaller? 2 is smaller. So 2 goes to the top and 9 still stays there and 8 comes here. Correct?
Yes.
That means, so inside the array, of course, we are not using any tree data structure. We are even the heap is also in the form of array. The given input is array. Even we are maintaining the heap also in the form of array. Now let's see in the form of array where the 2 will be. So initially 2 is inserting at this location. Now you are comparing 2 and 8 because this is the root node. What is the child node? The formula is like this, right? You look at the formula. So what is the formula for child? Anybody remember?
Um, yes.
So bottom up, you can start from
2n
basically.
plus
What's that?
2n plus 1 for the
It is I plus 1. If you want to get the childs basically, yeah. But let's start with the. I think I did not ask correct question. So the formula to find the parent. This is I minus 1 by 2. So basically you're inserting a 2 here you want to compare the value of 2 with its parent, correct? That's what we are doing. You inserted 2 here. 2, this is at 0th position, this is 1 and 2, right? So now you want to insert, you want to compare the value of 2 with its parent. How to get the parent? I minus 1 by
By
2.
2.
So 0, 2 is index, 2 minus 1 by 2, which is like 1 by 2 is equal to, so 0 index, like if you take the integer value, right? So 0. So that means 8 is at the parent. Like this is the 0th index is the index of the parent. So you compare only 2 with 8 and you swap those two. So this is the bottom up heapify. After this bottom up heapify, what is the array will look like? Array look like this. So 2 comes here and 8 goes here. See, we did the heapify. We did the kind of sorting, but not the normal sorting. In the normal sorting way, what will happen? 2, 8, 9, right? In the normal array sorting. But here we did not do the normal sorting. We did the heap sort kind of thing, right?
Yes.
That is the difference between normal sorting and heap sorting. Are you guys following so far? Now let's insert. Let me remove this. Like I already used most of the space here. Actually, we can do this. Yes, we can do this, but it may go down to smaller resolution. So let's try. Oh. So now we are going to insert 1. Let's see the magic after inserting 1. So this is exactly what I explained on the on the website, but we are doing one by one. We are doing one after the other. So if you insert 1 initial, this is our tree, right? This is our final tree. We will insert 1 just to the left of the 9, because that's what we already completed. First level, we completed second level. We just insert 1 to the left of 9, and then we'll do the heapify. That means if you insert 1 at this location, what is the index? This is 1 2 0 1 2 and 3. That means we insert 1 here, right? Let me change the color. So here you inserted 1 here initially. Now you want to compare, only you want to do the bottom up heapify from here to here and here to here, right? So 3 to 1, like what is the, how to get the parent node of this particular node? Same formula, right? 3 minus 1, 3 minus 1 by 2, 2 by 2. That means 1. Correct? So that means you just need to get compare with this value. This is the parent of this guy. See, 1 is the 9 is the parent of 1. Correct? So we'll compare these two values. You just swap these two values. That means what will happen? 1 comes here and 9 goes here. That means 1 come here and this becomes 9. Okay, are we good? No, right?
Yes. Then we need to one more sort.
We need to one more time. So we need to go all the way to the root. Then the sorting completes. The heap sort will complete. So now you are here. Now so the formula is same thing again. So 1 minus 1 by 2, which is 0. So we'll compare these two. That is the parent of 2 is the parent of 1. So 1 goes here. So 1 goes here. 2 goes here. So finally inserting 2 completed. Got it? So let's do the quickly. We will compare. We'll do the 1 is completed, and let's add the 3. If you add the 3, what will happen? So these two will become, I think if you add the 3, look at the magic here. If you add the 3, you don't need to do anything, literally, right? See, 2 is minimum and 1 is here, which is good. So adding 3 won't change anything. So heapify, if you heapify, no need to change anything, right? So your 3 will always be here. Okay. Now if you add 4, so where are you going to add 4? You are going to add 4 as a child of 8, correct? Now these two will be heapified. So the final tree will be look like this. 2, 3, and 4 will be here, and 3 will be here, and then oh sorry, I think 8 will be here, and then 9 will be here. See, 1, 2, 3, 4, 5, 6, right? So this is the, I think this is the heap, the final heap after inserting every elements. Correct me if I'm wrong. So the formula is always true, right? The value of the root is smaller than the value of the child. So 4 is smaller than 8, 2 is smaller than 3, 2 is smaller than 9. We are in a good shape, right? I guess clear so far?
Yes, yes.
Yes.
Now that is what the
Yes.
whole thing here, like bottom, sorry, not this one. See the bottom to heapify. This is the bottom to heapify. I can explain the algorithm itself. You know, so we can explain. So here is 124938. We will get the same thing, 124938. Yes. So that is the insert part. Okay. So let's look at the algorithm from the top. So we got the array here. This is the input. Okay. So now what are we doing here is we created a called min heap is the class we created. So this is the main algorithm. So let's look at the class. This is the class we created, min heap. Just like creating an array or creating a tree or creating a linked list. Let's say stack. If you are creating a stack, you are building a stack algorithm. If you ask you to create a stack using arrays or using a linked list, what do? You create a class called stack, and you create methods like pop, push, top, right? Those are the methods you create. So this is the min heap. We are building a min heap. So we created a class called min heap, and then we are so using arrays, right? So this is the building. I can say like building min heap using arrays. So you can use linked list or whatever, but that complicates the problem because you cannot easily navigate indexes, right? The reason why we are using array is you can jump around. You can easily jump from one location to the next. You can easily locate the parent node, right? By using indexes, you can easily locate the parent of this guy. You can easily locate the parent of any element. That's why we are using array. So if you look at here, we initialized array, but we created array, but we did not initialize because we don't know how many elements we want to initialize. So, and we are also maintaining two pointers, length and current. What is the reason is length will tell you, the total size, the total. Let's say we are creating a min heap of 1,000 elements. Okay, basically it will initialize with the 1,000 elements. That means when you are creating this min heap, since it is an array, you always need to mention how many elements you want to store. Okay, I want to store 1,000 elements, so you created 1,000 and the length equal to 1,000. But and let's say this is it's instead of integers, let's say these are the integer is there, but let's say the employees objects. Of course every object can contain an integer with an employee ID. So now you want to create a company with 1,000 employees. You say 1,000 min heap, create a min heap with 1,000, but you hired only 100 employees so far, or maybe 150 employees so far. So that will tell you the current. That means currently how many elements are there in the min heap. So this is the max size. So you can insert only this many elements, but the current will tell you where to insert or the number of elements. So right now 0. When you create the min heap, there is the first element. You can, when you're asking me to insert, I will insert at the 0th position, right? So that's what it is, insert. So this is the insert algorithm. So you're inserting, you want me to insert the value v. So if current equal to length, if the current becomes length, that means heap is full. You cannot insert anymore, right? So if the index of the current equal to length, so you already inserted 1,000 elements. Let's say you created 1,000 min heap with 1,000, so heap is full. You cannot insert anything. Otherwise, what you do? This is exactly what we discussed. Current will tell you where to insert. So right now 0. we are putting at that location, and then we are doing bottom up heapify. This dot bottom up heapify. And then once you complete that heapify, you are incrementing current plus. That means current will give you where to insert. So the current value will say, okay, when you are asking me to insert, I will go and insert in that particular location. That means the first empty location available in the array. Current will point the first available empty location in the array. Okay, so that's why we have to increment. Once you complete the whole insertion operation, you need to increment, so that next time if you're asking me to insert, I will insert at that location, and then I will do the bottom heapify again, right? And here is the bottom heapify. The algorithm is like this. As I said, we will start with the current location. We'll start, let's say you inserted 3. When you insert 3, what you do? So you compare with this parent, right? So that's why you start at the current, and then you go all the way to the parents, right? You need to go jump into the parent. That's what it is. At created I equal to current. You start with the value where you inserted. I just inserted at current, and then I started at that location. As long as I is greater than 0, okay, take the parent node of I. Take the parent and compare the value of I, A of I, and A of parent, right? So you started at that location and you take the parent node and comparing. If this value is smaller than the value of the parent, swap those values. This is exactly what we did, right? So we inserted 8. So what we did here? So this is, we started here and we compared with parent, and then we swap those values. So 8 comes on the top and 9 goes to the bottom. That's what we are doing. This is a very simple swapping algorithm. You all know that, right? I hope everybody knows this. A of I. So take the, so you are swapping the value I and j value to the I value. So putting in a temporary variable, and then you're replacing A of I because you already put it in a temporary variable, and then you can replace A of j equal to t, temporary value.
Yes.
It's very simple swapping algorithm, right? So we did that. So once you complete the swap, what you do? I equal to parent. Now you already completed. So as I said, let's say this is algorithm, right? So yeah, we have 8, 9, and 2. You inserted 2. Once you insert 1 here, that is what we do. So 1, you will insert 1 here. You compare these two. 9 goes here and 1 goes here. Then you compare. You need to compare these two. That's why I becomes, now you started it here. Now I becomes the parent. I equal to parent. Now goes back to the while loop, and I is still greater than 0. If I is still greater than 0, that means you did not reach the root yet. You start with some value, like if you have 150 elements, the I starts at 150. You just inserted 150th element. I starts with 150, and what is the parent of 150? Can you tell me where will be what is the index of the parent node if it is 150? The child is at 150, right? You have really big array, and here is the 150th node, means like 149. 149 is the index of the 150th node, right? Now where will be the parent?
75.
75. Yeah, I
149
think so.
minus
149 minus 1
by
by
2.
2. So 148 by 2, right? 74. Yeah, 70, this is basically 150 by 2, 75. But since, because we are wide is 74, it starts with 0, right? So you insert here and you directly go to that 74th element and you compare those two. You no need to compare with anything in between. That is the beauty of this heap sortify. Just please try to understand why we are doing all these things. The thing is, we want to make the comparison easy, and we want to make it the faster. It's the order of log. That is why it is order of log n. It's not order of n. You're not touching the other elements between. You're just comparing. You just added here. and we are taking the root of it and you exchanging those values if which one is smaller. If this is bigger, you don't need to do anything. If this is smaller, we are good. We just stop that. You can stop the whole thing. So that's what it happens. Swapping only requires as long as the element at this location is smaller than the parent. If the element, if this element is bigger element, right, it won't do this swapping. It will just simply, the I becomes 74 and it compares with its parent somewhere here, right? 75 by 2 something. So it will compare, but it won't swap. So the swapping only happens if the value you inserted here is smaller than the value of the parent. Okay, is it clear so far, Arvind and
Yeah,
Yes,
yeah, Suresh.
finally at the end of this whole heapify, we are good, and the tree will be in a heap, and the smallest element on the top. So that's good. So now get is, I think I called as get. Basically, get means it will give you the top element, and basically it's removing. You can also say get means like this will remove the top element and
top
make
means
sure
the minimum value, right?
minimum value. Yeah, yeah, top element or minimum value, and make sure the tree is again a heap. After that is very important. Taking minimum is just like, okay, take it. So the problem here is, so here is the thing. If the current is 0, you know empty heap. Oh, I think it's not. I think I did a mistake here. um because if the current is 0, there could be an element at the 0, right? We should not say, oh, that maybe that is the reason in the algorithm they started with 1. In the top here I just found, like, yeah, see, the peak of the heap, they started with 1. But if you start with 1, our formula will change. So it should be like, the parent formula will be like I minus I by 2 rather than I minus 1 by 2, I think. Let's see. So if current is 0, I'm saying empty heap. Otherwise, what I'm doing here, I equal to 0, and I'm putting at the 0th element. Oh, that's right. That's that's right. This is right, I think, because if current is 0 means what? What it is saying? Current equals 0 means, it means the next element will be stored current at 0th location. So next element will be stored at 0th location. What that means? That means there is no elements, right? If the current value is 5, let's say, then it will be, the next element will be stored at the 5th location, right? So if you look at here, when is the current 0? Current equal to 0 when you initialize the heap, correct? As
Yes.
soon as you insert an element, as soon as you insert first element, at the end of the algorithm, we are just incrementing current. So if you have one element, what is the current value?
2.
No. If you have one element in the tree, so you just inserted the first element 9. So after that, after inserting 9 means you will put 9 here. Then what is the value of current at the end
9.
of the whole thing?
9 is the
No, the
current.
current represents the location, the index where the next element needs to be inserted. This is what current means. Current means not the top. Current means not the index of the top. So what will be the current after inserting 9 into the heap? Can anyone tell?
Index of 1.
Exactly. So current becomes 1 because next time when you're asking me to insert an element, I will just put the value at this location. Of course, I will do the heapify, but initially I will just put the element here because the current will tell you where I need to put the next element. Because we created array with 1,000, like the whole size is 1,000. You can insert 1,000 elements, but where do you want me to put? That will represents the current. Are you guys following so far?
Okay.
Yes.
So
Yeah. Yes.
that is why we have this condition. If the current is zero, what is meant by that? Current is zero means there is no elements, right? Because current will be zero when the next day, if I just created an array like this, if I created an empty heap without any elements, initially I will say current equals zero. Because when you ask me to insert 9, I will simply put 9 here. That's why if the current equals zero, that represents empty heap. Next element is goes to the zeroth location. So if the next element goes to zero means there is no elements. So now let's do this. If it is current is not zero, that means what we need to do, I equal to 0 and result equal to a of I. So basically this is the result which we want, right? We want to return the value at the zeroth location. That's why we are putting 0. Now current is something. Current is, you know, 10 or 15, we don't know. So now what we need to do, as I explained here, the bottom up heapify. When you're removing an element here, right? I think yeah, here you want the first element, 3 will be removed. Once you remove the 3, what we need to do is we need to take the last element and put it to the top. How to find the last element? Current minus 1, isn't it? Because current will tell you where to insert the next element. Following so far? I know it is a little complicated.
Suresh, I have one question here.
Sure, yeah, go ahead.
In all these example, we are starting from uh, bottom to top. Can we go other way around, like from top to bottom?
That is a good question. Top to bottom, you can go, but the problem is that will increase the complexity. That means at the point of removing, you mean like if you remove 3,
Yeah, yeah. Then we
yeah,
can compare between 5 and 8, which one is smaller, so we can push that one to.
yeah.
Push.
I even I thought the same thing, but I think definitely that try it out. It will not be order of login. It will be more than order of login, I think. Yeah, the
Okay,
reason I
okay.
still need to find why we are doing like that. We can do that. The reason is, let's say you are comparing these two, right? You goes 5 goes here. Okay. Now what you do? 5
Yeah.
goes to the top. Now what you need to do? You need to compare 8. Of course, let's see. So 5 goes here. What you need to do is you need to compare 8 and so you need to put somewhere in the place of 5, right? What you're going to put?
Mm-hmm.
Now, what you need to do is you need to compare 17 and 19. Yeah, yeah, I think that is still possible, I think. So you need to omit the 8 because you're done with 8. Now
Yeah.
you're removing 5, right?
Yeah. Yes.
You're removing 5 means like the 5 goes to the top. Now you need to remove the 5. Now you need to compare the childs of 5, 17 and 19, and then 17 goes in the place of here. Now again you need to remove the value at 17. You need to compare 25 and 100 and 25 goes to the top. I think it still works, but somehow I think maybe there is an implication. I still need to identify why we need to do it this way. But this is a pretty the standard way of doing it, I would say. Okay, try it
Okay.
out.
Yeah.
Try
I will
um,
try this one. This
yeah,
approach. Another one.
exactly. So um, this is top bottom to top heapify. So the reason this This is the way to do the top to bottom. The top to bottom is basically we will insert the last element at the top. Like you take the last element and put it at the top and then compare. Okay. So now what we did. So here is the last element, right? Current minus 1. So current will tell you where the next element will be. So I'm saying like current is 150. If I say 150, the next element goes here. That means where is the last element? This is the last element, right? This is the last element in the array. So take that last element and put it at the 0th location, because that we will update the index saying next element can insert at the current minus 1 position. This will replace the duplicate value. Basically what we are doing here is we are decrementing current to the this value. Since you already copied this value into the here, and then next element can go here. You don't want to waste this memory, right? At the same time, you don't want to duplicate. So whatever the value here, you're already placing here.